Hello everyone, I'm Typhoon. Welcome to another lecture. So think about the sounds you hear every day. People talking, dogs barking, or car engine revving. These sounds are much more complex than the simple tones we've been working with so far. Today we will analyze one of these real-world sounds, a human voice, and see how it looks in both the time and frequency plots. Before, we worked with basic tones. They were neat, clean, and easy to understand. But the world around us doesn't sound like that. Real sounds are full of energy, frequencies, and surprises. By studying them, we can learn how to handle more complicated signals in SDR. So let's jump into it. To make a room for our real-world sound, we will delete this signal source block, but let's actually create a new one, new kitty GUI, and here we are, and save this as, let's call human voice. And that's it. We will add a new block called WAV file source. So this block takes audio from a recorded file and feeds it into our flow graph. And here's how to set it up. We will add the file source block. We will open its settings and select the file you can download from the course attachments or resources. And here we will come to Typhoonix. No, it was somewhere in desktop. And here OSR US8 key Typhoonix.wav file. It's a relatively small size, by the way. And here we are. Click OK, and we will also add audio sync to hear the sound. Let's also add time sync. So this time sync, as you remember, shows how the sound looks like in a time domain, like as a waveform. And we will also add frequency sync. This frequency sync shows us the sound frequencies in a graph. Now let's connect this. Here, as you can see, we have red lines, which tells us something is wrong with the parameters, and blocks are not compatible with each other. That's because the sampling rate of audio file you are using, as you can see it, I named it as 8 key, so this means 8000. So we need to change the sampling rate of our all sync blocks to 8000. But before that, I want to show you something. Let's delete this, and as you can see, we don't have any problems with this audio sync. But it's obviously will works in a relatively different way. Let's test this. And here you can see it's like fast forwarding, and that's not what we want. So we will change it all the sampling rate to 8 key. $8,000 and 8,000. And we also need to edit this turn complex to float. That's why we are getting errors as well. Again. And that's it. After connecting everything, your flow graph should look like this. It's simple, but it packs a punch. Now, when you execute this flow graph,
the birch canoe slid on the smooth planks. Glue the sheet to the dark blue background. It is easy to tell the depth of a well. These days, a chicken leg is a rare dish. Rice is often served in round bowls. The juice of lemons makes fine punch. The box was thrown beside the parked truck. The hogs are fed chopped corn and garbage. 4 hours of steady work faced us. A large size in stockings is hard to sell. The birch canoe slid on the smooth planks. Glue the sheet to the dark blue background.
So, when you execute the flow graph, three things happen. First, you hear a human voice through your speakers or headphones. And here you can see the time domain plot. This shows a complicated waveform full of twists and turns. So as you can see, the FPS is relatively slow because I'm running this program in my virtual machine and my computer is slow. And the third you are seeing is the frequency domain plot, reveals a forest of peaks representing the many frequencies that make up the voice. So let's break it down. So in the time domain plot, before we saw smooth waves for simple tones in previous lectures, now the waves looks messy and unpredictable. This is because real world sounds like human speech are made up of many overlapping waves. And what you're seeing in this frequency domain plot, the peaks in this plot shows the frequencies present in the voice. You will notice that most of the energy is in this mid and lower frequencies where voices usually are. There are also some higher frequencies here which add detail to the sound. So the frequencies move and shift as the voice changes over time. So why is the frequency plot is important? So when the WAV file is played, the frequency sync uses a process called fast Fourier transform to break the sound into its individual frequencies. Without this, we wouldn't be able to separate and understand the different tones in the sound. This is one of the most powerful tools in SDR. It helps us analyze and process even the most complex signals. So, as you can see here, we can also zoom into signals like we did in previous lectures. And if you are feeling creative, you can record your own sound and analyze it. Here's how. You should use an audio recording software to record a sound, like your voice or a musical instrument. Save the file in WAV format with a sampling rate of 8 kHz, or adjust the flow graph setting for your other rates like 32 kHz or like 48 kHz. And load your file into the flow graph and see how it looks like in the time and frequency plots. You will discover that every sound has its own unique pattern of frequencies. So you might ask, why does this matter? Now that you've seen how to analyze real-world sounds, you are ready to take the next step. Most signals we work with in SDR aren't clean or simple. They're complex, just like the human voice we analyze today. By understanding the frequency domain, you can uncover hidden patterns and solve problems in your flow graphs. In the next lecture, we will learn how to shape and change signals using two powerful tools, gain and filtering. This will let you make a weak signal stronger and remove unwanted noise. These tools are essential for signal processing and will take your skills to the next level. My name is Tayfun. Thank you for watching, and I'm meeting you in the next lecture.